Hello everyone, I'm very happy to be here. Just before I start, just want you to know that this presentation is going to be made available online, hopefully today, maybe tomorrow. Also, a little disclaimer, as the title of this presentation suggests, these are the basics of deep learning, so by no means am I going to go through every aspect of deep learning. Yesterday it was mentioned that with machine learning methods we can do all kinds of things like classification, regression, estimation of probability density functions. So for this talk, I'll be only talking about classification. I'll start with a very simplistic example, and I'll build on top of it. Also, this presentation is intended for those who are completely new in the area. So for those of you who already started playing with deep learning, maybe some of the stuff, especially at the beginning, will kind of sound a little bit simplistic. Anyhow, everything that I'm be covering are things that are completely fundamental to understand deep learning. So we'll start with the very basic stuff, including some things that were kind of covered yesterday, but that is intended to see it a second time to really make sure that everyone is on the same frequency. Okay, so let's dive right into it, and I would like to start with a very simplistic example. So let's say that you have an hospital, and people come at the hospital, and they all go through the same protocol, which basically it's a very simplistic protocol. So each patient goes through the protocol where we take their body temperature and their cardiac frequency. Okay, so one patient comes in, you take body temperature, cardiac frequency, and then a doctor clearly assess the status of the patient and come with a diagnostic. Okay, so it could be a two-class diagnostic, healthy or sick. It's a very simplistic example. So we have N patient. Each patient went through the same protocol. So each patient is assigned to two observations. In this case, temperature and frequency, and we have a label, okay, a target. So this table, we'll call it D. This is what we call a labeled data set. Yesterday, during the roundtable session, we often talked about a labeled data set. Well, this is a very simple example of a labeled data set. Throughout this presentation, I'll be referring to data set as a letter capital D. The observations, since we have two observations, we have a vector of two elements. We'll call it X. And the target, we'll call it T. Okay, here we only have one target. Eventually we could have more than one target, but now it's only one. And by doing so, what did we do? Okay, mathematically that means we took every single patient and put it as a point in a two-dimensional space. And hopefully the first group of patients, those that were healthy, ended up living pretty much at the same place in the two-dimensional feature space, and the other ones are kind of further away. And somehow we can separate some of those healthy patients from the sick population. Now, still in my example, say we have a new patient that comes to the hospital and we would like to automatically assess his condition. Okay, is the patient sick or healthy? So what we're going to do, we're going to go through the same acquisition protocol where we will take his body temperature and his cardiac frequency. So that means that new patient will become a new point in our two-dimensional space. Let's say it falls over here. And then we would like to know is that new patient is sick or healthy. So one thing very simple that we could do is just to look at the nearest neighbor in this two-dimensional space and to figure out, you know, those nearest neighbors, are they sick or healthy? In this case, it would be mostly sick. So that would lead to a very simple classification method called the k-nearest neighbors. The trouble with that method is that it doesn't scale very well. Here we only have a two-dimensional space, which is a very simplistic example. In real life, let's say you had images, that feature space could easily go to the couple of hundreds of thousands dimensions. And in such a large dimensional space, k-nearest neighbor method collapse. So they don't work well. So we're going to do something else that was mentioned yesterday. The idea is to separate mathematically the space in two separate areas. Okay, so we'll have the area, mathematically, we'll have the area of the sick people and mathematically the area of the healthy people, like this. And depending on which side of this linear line, linear separation plane, the new patient falls, we'll be able to make a prediction. Is the person is sick or healthy? Now, more formally, that means we have a function that I will call y that takes as input a two-dimensional point, x, and that returns a target, okay, a class label, which would be, in this case, healthy or sick, okay? Now, the question is, how do we get to split the feature space mathematically? Okay, that, again, that was mentioned yesterday, but I just want to go through the math very slowly so it becomes crystal clear for you, because at the beginning it's going to be quite simple, but then things are going to add up, and it's very important to understand. So let's go back to a very basics, the definition of a line, okay? So we all saw that equation. I was 12, I think, the first time I saw that equation. So y equal mx plus b. So m is the slope, and b is the bias. Okay, that's the equation of a line. So I think everyone are following me at this point, hopefully. So the slope is the ratio of delta y, delta x. And the bias is the distance to the origin. So if the bias is 0, that means your line goes to the origin. Now, if we replace m by the ratio delta y over delta x, and then we reorganize the term, we get that equation here. Again, we don't need many years of study in the university to kind of understand that equation. Then we can just put everything on the right-hand side. So we have an equation that essentially, if any point that falls onto this red line, if that 2D position is fed to that equation, this equation will return 0. That's what it means. So just to simplify the notation, we'll just do a few renaming variables. First, delta y, we'll call it W1, minus delta x, we'll call it W2, okay? And the bias, we'll call it W0, okay? So W are the weights or the parameters of your model. Then that means this same equation becomes this. W1 times x plus W2 times y plus W0. And we'll do another renaming. So instead of saying x and y as the two axes, we'll go with a different naming convention. We'll call it x1 and x2. Why? Because those are essentially features. So we live in a two-dimensional feature space. Eventually, if we want to add another feature, we'll call it x3, another feature x4, and so on and so forth. So this way, we have this equation here. So W1 times x1 plus W2 times x2 plus W0, okay, which is the bias. Again, if W0 is equal to 0, then that means that this line goes through the origin. Okay, so far so good. So we have this equation here, okay, that I called y. Again, that's our equation. I added the subscript w to say that that equation depends on a vector of parameters w, so w0, w1, w2, and it takes as input a two-dimensional position x. So any point on this red line fed to that function y will return 0, okay? Now, something very interesting is that, as I said, W0 is the distance to the origin. So if W0 is equal to 0, that means this line goes through the origin. But W1 and W2, and that's quite simple to prove, W1 and W2 is the normal. So it's a vector that is perpendicular to the line. And that essentially says, you know, what is in front and behind this line. So if you take a point in this two-dimensional feature space that doesn't fall on the red line, but instead fall in front of the red line, and you feed it to this equation, you'll have a result or a score that is larger to 0, okay? And if you have a point that is behind the line, you'll have a score that is negative. Okay? This is what you call a classification function. Okay? So if we knew the correct parameters, if we want to know if a point is in class 1 or in class -1, we just have to look at the sign of this function. Okay? Okay. Okay, thanks. If we take some very concrete examples, so let's take those values, W1, W2, W0. Okay, W1, W2, W0. Okay, just to convince ourselves that it works, that the math works. So just replace W1, W2, and W0 by those values, okay, that you see here by 2 and 3, and you'll see that this equation returns 0. If you replace x1 and x2 by 1 and 6, you'll see that the score is going to be negative, and let's say another point here that is in front of the line, you'll get a score that is positive. Okay? So that equation, that very simplistic equation of w1 times x1 plus w2 times x2 plus w0 can be summarized by what we call a dot product. Okay? So if we take two vectors that each contain 3 elements, so w0, w1, w2, and the other vector is x1, x2, that we augmented by a value of 1 in order to include bias. So if we do a dot product, it means you multiply each element of those two vectors and then add it up. That's the definition of a dot product. Then we have the equation of a line. Okay? And that line can be used as a classification function, but because everything that falls in front of the line, you get a positive score, and behind the line, you get a negative score. So that's a dot product. And in supervised machine learning, yesterday it was mentioned SVM, for example, support vector machine. It's based on this very simple observation. So this is x prime, which is the input vector, so the input feature that we augmented by a value of 1. And this is vector W, which essentially are the parameters of your model. And in fact, this dot product can be summarized by this notation here. So it's that vector that we transpose, so that way it's a line vector times x, which is a column vector. So by multiplying a line vector but a column vector, it's end up being a dot product. So just for simplicity, I'm going to drop the prime here on the right, okay? So let's keep in mind that each time you see a notation like this, you have a linear classification, okay? It's a dot product with the bias included into the vector x, okay? So for the remaining of this presentation, each time you see a dot product, especially at the end of a network, keep on thinking that this is a linear function. Okay, so we're doing machine learning, so somehow down the road we have to learn something. So with a training data set D, so the end patient that we have, so each patient we know the body temperature and the cardiac frequency, and we know the status of the patient, so the target. The goal is to find the best parameters, W0 and W2, W1 and W2, that would best separate the two classes, okay? So that's the goal of machine learning. In order to do this, before we start learning anything, we need to ask ourselves, how do I know if a model is good? Yesterday, Carol mentioned that for this, you need to have a loss function, okay? That function will essentially tell you how good your model is. So that loss function, if you look at it, so it's a function that I call L for loss, that takes as input two things, your model here, so your line essentially in 2D, and D, your label data. And essentially, if your line separate well your two classes, your loss should be very close to 0. At least it should be minimal. Now, if you have a solution like this, where you have a couple of points that are misclassified, but most of the points are well classified, well, you should have a loss that is not too large, but certainly larger. And if you have something like this here, where you have a very bad model, the worst model is a model that would behave like noise. So a patient comes to the hospital, and then you flip a coin, and you tell that patient you're sick or you're healthy. So that is the worst situation. So in this case, the loss should become very large. So far, what do we have? We have a training data set, D. We have a classification functions. So far, it's a very simple function, just a 2D line. We have a loss function, okay? We haven't defined it yet, but we know that we need a loss function. And then the goal is to do training, which is to find this vector of parameters that would best minimize the loss function. Okay? Okay, so today we're going to see a couple of methods. We'll start with one that was mentioned yesterday, the perceptron. Then we'll go through logistic regression, then multi-layer perceptron, and then convenance. Okay? So the perceptron. Perceptron is absolutely not new. It goes down to the 1950s. And that's the actual machine. Back then it was not programmed. It was actually implemented with hardware. So what is the perceptron? So far what we have seen is that we have data in two classes that each point live into a two-dimensional feature point. Hopefully there exists a line that can linearly separate those two classes, and that line is defined by this equation here. That's what we said so far. Well, that model can be graphically represented as follows. So on the left here, we have nodes, and those nodes contains input values, so 1 for the bias and x1 and x2 for the features. And those nodes are then connected to another node. These connections, these arrows, contains parameters, values. And that middle node here, okay, right there, is a dot product. Okay, so that graphical representation represents this equation on the bottom right. And at the end, at the right, you have the score of the function. Okay, positive if you're in front of the line, negative if you're behind of the line. Now, the perceptron doesn't return a positive, an arbitrary positive value and arbitrary negative value. It returns strictly +1 or -1. +1, you're in front of the line. -1, you're behind the line. So how do we get to do this? It's with a sine function. So the sine function, it's a very simple function. It returns +1 when you feed it with a positive value and -1 when you feed it with a negative value. So this dot product and this activation function is any function that is nonlinear, okay? You can combine it together, and that will give rise to the famous neuron, okay? So that's what we call a neuron. 99% of the time, when we say we have a neural network, 99.999% of the time, when we say we implemented a neural network, this is what we mean by a neuron. So by no means does that neuron, this is usually the point in the presentation where I open a parenthesis on the notion of neuron and the actual neurons that we have in the brain. Obviously, this has no connection, no real connections with what we actually have in the brain, okay? It's like when we say a plane is like a bird, okay? Yes, there's a semantic connection between a plane because the fuselage is like the body and you have those two wings, but that's pretty much it. I mean, a bird has leaf, a plane doesn't have leaf. A bird eats insects, a plane doesn't eat insects, and that is fine in this way. That's the same thing with neural networks, okay? We don't actually implement neurons that we have in the brain, and that is why we always have to be very cautious when we say, usually scientists never say this, but sometimes non-scientists say we are trying to re-implement a new brain, okay, with those kinds of neurons. This is absolutely bogus and phony baloney, okay, so please don't say this. In fact, more and more we see in publication the term neuron being replaced by the term of node, which is more, let's say, neutral. In this class, I'll be talking about neurons, but you can also think about nodes. Okay, so far we have a training data set, we have a classification function, which is a graphical model. We have a loss function, and we want to train that model, which is find the best parameters. Okay, so far so good? So linear classifiers have their limits, obviously. So if everything was linearly separable, then life would be far too easy and too boring. In reality, we have situations like that. Okay, we have classes that are roughly separated, but not well separated. Okay, and if you use a linear classifier in a situation like this one, you'll end up having very large error. And for many applications, this is unacceptable. So what can we do? Okay. Well, there are three typical solutions to that problem. The first one is to acquire more observations. The second one is to use a nonlinear classifier. Yesterday it was mentioned the decision trees. Decision trees and random forests are nonlinear classifiers. Or you can do something very interesting, which is to transform the data. You take the data that lives in a space that is non-linearly separable, and then project it to a new dimensional space with some magic. We call it the deep learning magic, or the neural network magic. You transform it to a new dimensional space where data is linearly separable. Yesterday, Carol mentioned about the kernel SVM. That's what kernel tried to do. They tried to take the data, project it to a place where things are linearly separable. So let's first start with what can we do. What is this notion of acquire new observation? Well, you know, maybe if I go back to my first example, maybe after all, just taking the body temperature and the cardiac frequency is not enough to well, you know, discriminate between those that are healthy and sick. So that's too simplistic. So maybe let's say we'll ask a patient for their level of a headache. Do you have an headache? Okay, if yes, can you tell us what is the level of that headache between 0 and 10? So this is something that is sometimes done in a clinic. So that means your observation, so and it's very important that every single patient goes through the same protocol. So that way each patient is being assigned 3 values, okay, the body temperature, the cardiac frequency, and the headache, and the target is still the same. So that means instead of having a 2-dimensional feature space, we now have a 3-dimensional feature space. And hopefully in that 3-dimensional feature space, things are linearly separable. So what happens if we want to do this to our perceptron? Well, the perceptron, that's the beauty of the thing, accommodates very well to that. Okay? It just, at the end of the day, it boils down to having more nodes at your input. That neuron, that yellow neuron in the middle still is a dot product followed by a nonlinearity. Here's a sine function. The equation of the equation becomes the equation of a plane, okay, in a 3-dimensional space. You still have that vector, okay, which is depends on W1, W2, W3. W0 is still the bias, so the distance of the plane to the origin. And of course, you can have a k-dimensional feature vector, no problem. It generalizes, the model generalizes very well to that. And this we call an hyperplane, okay, because we are in more than 3-dimensional space and we cannot visually represent it, okay. So the goal, as I said, the goal is to train the machine. So the goal is to have that function here, okay, that is the equation of an hyperplane, that each time I take one element of this training data set, let's say xn, that function will be able to replicate the target of that element. Okay, that's our goal. And the goal is to find the best weights W that will minimize the loss function. And look at that loss function. So that loss function here, maybe this is going to work. Okay, that loss function here is in fact a summation over each element of your training data. So it's a summation over each of your patients. You have n patients, and for each patient, you look at what is the class that your model predicts, and does that class correspond to the actual class? So, and that is a very typical optimization problem. So as I said before, we need a loss function. So in the case of the perceptron, Before we go back to the perceptron, so the idea of optimization is what? When we have a good function like this one, we have a small loss. When you have a bad one, we have a large loss. So let's look at this representation. Okay, so at the beginning I said, you know, we live in a two-dimensional space and we have three parameters, W0, the bias, W1, W2. So let's take an even simpler problem. We don't have a bias, okay? We assume that your line goes through the origin. So that means you only have two unknowns, W1 and W2. That's what we have here, W1 and W2. And for each combination of W1 and W2, you have a different line. And for each line, you'll have a different loss, okay? So some lines will perform very poorly on your training data. That means you will have a very large loss. And some lines are going to perform very well. So that means your loss is going to be close to zero, okay? So this is what this graphical representation shows. So the goal here is to find the best solution, okay? Out of every possible solution, we want to find the one that would minimize the loss. How do we do this? There are different ways of doing this, but typically in neural networks, we assume that the best solution is where the gradient, or if you want, the slope of this loss function is equal to zero. And how do we reach that point? How do we find that point? Well, a typical approach is to randomly initialize your weights, W1 and W2. So that means you take a random point somewhere. Since it's a random point, it's very likely that it's going to have a large loss. It's going to be a bad solution. But for that point, we know how to compute the slope. We know, what is the gradient of that position on this loss function. So we can take a step towards where the loss will be the most minimized. So we're going to take a first step that will leave us to a new position in the W1 and W2 space. At that new position, we can re-estimate the loss, and for that loss, we can estimate the gradient, and then we can take another step, and another step, and another step, and so on and so forth, up until when we reach the global minima, okay? So this is what we call the gradient descent. So we want to reach the point where the gradient is equal to zero towards an equation that looks like that. So each vector W is going to be updated in an iterative fashion, okay? And that each iteration will take a step towards where the gradient is pointing into the most negative value. That is why we have a minus here. And the eta parameter is called the learning rate. This is a very typical hyperparameter that one has to somehow set for his model. So what kind of loss are we going to implement? So first, we need to have a loss that you can derive. If your loss is non-derivable, then those kinds of approach will not work. You will have to you will have to use different kind of methods like reinforcement learning. That's what it does. But typically, you need to have a loss that you can derive. So the loss for the perceptron is called the Perceptron Criterion. So it follows from a simple observation. So remember I said, you have a line, and a point that falls in front of the line will have a dot product that is going to be positive, and a point that falls behind the line with the dot product is going to be negative. Okay, that's what I said before. Well, a wrongly classified sample is one where the sign of the dot product is going to be different than the sign of the actual label, which is +1 or -1, okay? So if you take the dot product times t, okay, that equation here, dot product times t, a wrongly classified sample will always return a negative value, okay? Now, if you take minus the dot product times t, then this is always going to be positive for wrongly classified samples, okay? So maybe you have to look at those maths more carefully, but the loss for the Perceptron criterion is the following. So it's a sum over each wrongly classified samples, and for each wrongly classified sample, you take the dot product times t. This will always be negative, and then you change a sign, and you sum over each wrongly classified sample. So if all of the samples are correctly classified, then your loss is 0. okay? And if lots of samples are wrongly classified, then you have a long summation of non-zero values. So your loss becomes very large. So if you take a configuration like this one, your loss is, I computed, it gave 464. It means nothing, okay? It just means that you're far from an optimal solution. So far we have a training data set. We have a linear function that is a dot product that can be graphically represented as follows. Now we have a loss function. That loss function, we can derive it, and so we can implement a gradient descent and find the best hyperparameters, find the best parameters W. Okay, so we have that formulation that we sometimes see in the literature, argmin. So that means among every W's possible, you want to find the one that will minimize the loss. That's what that is what argmin means, and we want to reach the point where the gradient is equal to 0. Okay, where the slope of the loss function is equal to 0. Okay, is that clear? Everyone is following me? Okay, good. No one is sleeping? Good. So this is the gradient descent, and this leads to a very important algorithm. Those who will have an end-on session, this is a very important buzzword, SGD, stochastic gradient descent. So the simplest form of a stochastic gradient descent is as follows. So you iterate a certain number of times. Okay, typically you have to specify the maximum number of iteration that you want to you can tolerate. So that's K, and then you have a second for loop that goes through every observation in your training data set, so every patient, and then for each patient, you look at the loss, compute the gradient of the loss, and then slightly improve the parameters for each of the patient. And once you have visited every patient at once, then you reach a new buzzword that is called an epoch. Okay? An epoch is when you go through your training data set all at once. This is one epoch. And then if you start all over again, it's going to be another epoch, and then another epoch, and then another epoch. So for the perceptron, we have the loss here, okay, minus the dot product times t, the gradient of L with respect to W. So since W times X times T is a linear function, so the gradient with respect to W is just X times T. Okay, so the gradient is very easy to implement. So the stochastic gradient algorithm, the simplest stochastic gradient algorithm looks like this. So it's a for loop over n iteration, then a for loop over every single element in your training data set. And then for each element, you look at if that element is wrongly classified. If it's wrongly classified, you update the W's. If it's not wrongly classified, you do nothing. Okay? So eventually you'll reach a point, if the data is linearly separable, where every point are going to be correctly classified, and so the parameters of the model are not going to be optimized anymore. So that means you've reached a global minimum. So the learning rate has to be chosen carefully. Too low, you'll have a very slow convergence. Too large, it might diverge. Sometimes people use a fixed learning rate. Sometimes maybe this afternoon you'll see the learning rate. You can decide to have a learning rate that decreases over time. But just keep in mind that too low is not good, too large is not good either. Okay, so this is our perceptron loss, the perceptron criterion, which mathematically can be summarized here, which is a summation over each of your elements in your training data set. And then you take this function here, minus t times w times xn, okay, the dot product. And if that dot product, that negative dot product times xn is negative, that means that point is well classified. You just maximize it to 0. So those two equations are absolutely identical, okay? Absolutely identical. Now, if you add a 1 to that second equation, this is what we call the hinge loss or the SVM loss. And this one, you know, where does it come from? It comes from what Carol mentioned yesterday. It's the notion of margin, okay? But at the end of the day, it's absolutely similar to the perceptron criterion. Okay, so so far so good. we're not doing much. We're just linearly separating data, but we're putting some very fundamental stones on which we're going to build our house. We're currently building our deep learning house. So how do we get to have a multi-class perceptron? Okay, how do we, so far we had 2 classes, but in reality you can have more than 2 classes, okay? You can have not just sick and a healthy patient, you could have normal patient, mild cognitive impairment patients, and Alzheimer's disease, okay? So that could be 3 typical classes. That's an example. You could have, you can think of more classes. So the beauty of this multi-class perceptron is that at the end of the day, it is still the same model. So what did I put here? Pay attention to this graphical representation at the top right. You have this red line, okay, which is a linear classifier with this arrow that shows in which direction things are positive. You also have a blue line and a green line. So that means you have 3 classes. 3 classes means 3 linear classification function. 3 linear classification function, that means 3 dot products. 3 dot products, that means you need 3 nodes that perform a dot product each one. Okay, that's what we have here. Okay, each node there, this one, this one, this one, corresponds to a dot product. And as I said, a dot product corresponds to a linear classification function. So you just have to multiply the number of neurons. So what do we have here? The output of that neuron here is going to be that dot product, which is summarized by this equation here, which is our linear function that we had seen before, okay? And the second neuron and the third neuron. And that series of function, so our neuron, our system will output 3 values, and we'll take the neuron with the largest values and assume that this is the correct class for the observation. So let me, so at the end of the day, those 3 dot products can be summarized by a multiplication between a matrix and a vector. But this multiplication of matrix vector can be understood as 3 different dot products. Mathematically, it boils down to the same thing. So let me just take a very simple example. Let's say we have that point in the 2-dimensional space, and we want to know in which class to which class it belongs. So you see that it falls in front of this red line, but behind the green line and behind the blue line. Okay. So what can we expect to have? Well, let's say these are the parameters of our model. We replace x1 and x2 by 1.1 and -2. We perform 3 different dot products, or if you prefer, a multiplication between a matrix and a vector. At the end of the day, it's going to give us -6. So you're behind the first separation function. -9, you're behind the second one, and plus 8.2, and that means you're in front of the third line, right? The third separation line. So that, obviously, that point seems to be in class 2, okay? So the multi-class perceptron loss is, again, a summation over every wrongly classified samples. I'm not going to get into too many details for that function, but essentially it's the difference between the dot product of the wrongly classified sample, okay, the wrong class minus the correct class. And for this, we can easily compute the gradient again. So if we can compute the gradient, that means we can implement a gradient descent algorithm. And the gradient, the stochastic gradient descent of a multi-class perceptron looks like this one. Okay, it's a series of epoch. For each epoch, you go through every element of your training data set. Okay, and for each element, you look at what your model give you, okay, the prediction of your model. Is the prediction correct? If it's correct, you do nothing. If it's not correct, you just update your parameters of your model. Okay, the perceptron is very simple. That's great. It's just a few lines in Python. It's very easy. It's typically the first homework my students have to implement in the machine learning class. It does not assume that the data follows a specific distribution. So it's not the kind of algorithm where you start by saying, let's assume that everything is Gaussian, okay? Here we just assume that everything is linearly separable, okay? The trouble is that, so there are two important limitations. First, there's an infinite number of perfect solutions. So as long as a line correctly separate the elements of the two classes, that function is considered to be optimal. So it has a zero loss. So mathematically, you have an infinite solution. But intuitively, as it was mentioned yesterday, some solutions are better than others, especially those that have a large margin. Sometimes you might end up having suboptimal solution, especially in the presence of outliers. And the perceptron, and that's the most problematic aspect of perceptron, when data is not linearly separable, the perceptron will never converge. And in fact, it's want to keep on oscillating, because you'll never reach the point where you have only well-separated data. Okay, so there are two very famous ways of improving the perceptron. So the first one is to find a new activation function. If you have a new activation function, that means you have a different scoring function, a different classification function, and thus you need to have a different loss. Okay, so that's first solution. Or you find a new network architecture. Okay, so this will give rise to a so-called logistic regression, and this will give rise to multi-layer perceptron and CNN. And logistic regression builds on top of perceptron. So if you don't understand perceptron, if you don't understand what a gradient descent is, what a loss is, it's very difficult to understand what the logistic regression is. And if you don't understand what the logistic regression is, it's very difficult to understand what's a multi-layer perceptron and CNN, because it builds on top of it, okay? Okay, logistic regression, what is this? So are there any questions, or is that clear? If someone has a question, I will. No? Okay, okay. It's a joke. Ah, okay, there's a question over there.
Hello.
Sorry, I didn't get what's the difference between the stochastic gradient descent and the usual one?
Oh, the stochastic gradient descent is the reason why we call it stochastic is because you go through each element of your training data set, and for each element you compute a gradient, but just associated to that specific element. So a real gradient descent, typically you would consider your entire training data set. In fact, mathematically, you should consider every possible element in an infinite training data set. Obviously, we don't have access to that. So that's why we call it the stochastic. Okay, why stochastic? Because there's no, stochastic means there's some randomness. There's no randomness on those algorithms. It's just because since you're looking at every point, and those points can be kind of noisy, the gradient descent is never really gentle. It never just flows gently down to the global minima. It just goes like a little bit left, a little bit right, and then left again, and then left again, and then right, and then left. It zigzags down to the global minima. So that's why we call it stochastic.
Is there other questions?
Yeah. Ah, okay.
You didn't mention if the loss function need to be convex. Is it something which
is
necessary?
This function here is convex.
Okay.
Many functions, you cannot prove that they are convex. And often, I mean, for a long time, people thought that was a problem. Okay, your function is not convex, so you might find a local minima that is not a global minima. So local minima means that your algorithm thinks you have reached global minima, but it didn't. So there are different algorithms that are relatively robust to that. But there was a couple of papers published not so long ago showing that when you have, here my example was in a two-dimensional space with the W1 and W2 and W0. So let's say you have three unknowns. So this is a very low dimensional space. In reality now, neural networks have over 1 million of parameters. and in that 1 million dimensional space that we can not even imagine. The only thing we can do is to take this down to a 3-dimensional example. That's all we can do, right? But in a 1 million dimensional space, things are very complex. But the thing is, it was shown that you don't really have, those local minima are very rare. What we most of the time see are dimensions where the loss goes high, but some dimension where the loss goes down, okay? It's very unlikely if you have 1 million dimension that each of those dimension has a second derivative that points to the positive value. This is very unlikely. So that's why we have mostly points that some dimension whose loss is going up, but other dimensions whose loss is are going down. And that is pretty much the reason why, if you take pretty much any neural net, let's say a famous AlexNet algorithm, this one has a large number of parameters. Well, anyone can train it with a random initialization, and it always converges to something that looks like global minima. But it's a very good question.
Other questions?
Yeah. Oops. Okay.
They are not sleeping, huh?
They're not sleeping. Okay, good.
Is the choice of the loss function tied to the choice of the activation function?
Yes,
meaning?
absolutely.
Okay.
That's a very good question, and in fact, it's the topic of the next slides. So see, you're really not sleeping. Okay, so maybe I can just, okay, maybe one
Okay, last question and then
okay,
we
well, last question, and then we're
Okay.
going to move on.
Sorry, on the slide where you separate 3 classes.
Yes? Oh, you want me to go back to where I separate the 3 classes? Here?
Yes. So the lines that I used to separate the classes, they separate the dots.
These lines here, and these
Yes.
lines there, and these lines there, yes?
So they, if those colored sectors, they go beyond the.
Okay. Yeah, that's okay.
image,
I skipped through one little detail. So that green line with this arrow is the actual representation of the separation function, okay? That red line with the arrow and that blue line with the arrow is the other 2 separation function. Now, this color, red color here with a V shape, this green color here with a V shape, and this blue color here with a V shape, what does it represent? If you take, for example, that red section with a V shape, let's say this point here, okay? This point is behind the 3 separation line. So that means if you take a point there, compute a matrix multiplication, at the end of the day, you're going to have, you'll end up having 3 negative values. But the score in the red function, the third negative value, is going to be less negative than the other ones. So it's going to be like maximum compared to the other ones. So I don't know if you, if that's, because you were wondering why this point is behind that line and yet is being classified as being green. Is that
Yes.
the question? Yes. So this point is behind the red line, the green line, but it is also behind the blue line and behind the red line. So since it's behind all 3 red lines, the score of the 3 classes are going to be negative, but the score for the green function is going to be less negative than the other ones. And what is important here is the maximum. So you're looking at the score that is maximum, not necessarily the most positive. It's the maximum one. Okay, so if you have a score of -1 for one class and -2 and -3 for the other 2 classes, well, you'll come to the conclusion. And this is unavoidable, in fact.
Okay.
Okay, very good question.
What we
kind
can
of
say is
stumbled.
that for each point of the space, you affect the color of the closest line.
Exactly. Okay, so the logistic regression. So here we're going to use a different activation function. So we have exactly the same structure, but instead of using a sigmoid, a sine function, we'll use a sigmoid function. Okay, that's another very important buzzword, the sigmoid buzzword. Sigmoid activation function. So what does this activation function looks like? So the sine function is 0 for everything it was -1 for everything that was negative and +1 for everything that was positive. Here it's a function that goes from -infinity to +infinity, and that takes any value between -infinity and +infinity between 0 and +1. And at the origin, okay, if you feed, so you have sigma, if you feed 0 to sigma, sigma will return 0.5, okay? So what does that mean? Okay, so you have a new type of neuron that is a dot product with an activation function, but now your activation function is a sigmoid, okay? Historically, that sigmoid function was fundamentally important. So your function, what is the output of your function? It's sigmoid of a dot product. Now, what's going on here if we implement that function? Well, you'll see that any point that falls onto the separation line, okay, will correspond to a score of 0.5, okay, because you will feed sigmoid by 0. So every point that will be in front of the separation line, the sigmoid will return a value that will be larger than 0.5, okay? And if you feed your sigmoid function by a large value, then your sigmoid function will return a value that is very close to 1. And if you're well behind the separation line, the sigmoid function will return a value that is very close to 0. So I don't know if this rings a bell, okay? What kind of function that goes from 0 to 1? Okay. Mathematically, the sigmoid function has a gentle shape that allows us to mimic what we call the posterior probability function. Okay? You have a probability, right? What is the probability of that point of being in this class? 95% chance it must be in this class, okay? Or let's say 10% chance, so it's unlikely to be in this class. So here's a very simple example. Let's say your parameter, you train your model. The model is very well trained. These are the parameters that you have. And then you take a point here. You compute the dot product. That will give you -1.94. You feed this to a sigmoid function. And the sigmoid function returns 0.125. This can be interpreted like a probability value. So there's 12.5% chance of that point to be in the positive class, okay? Which is smaller than 0. And if you have a point that is right onto the separation line, you have 50-50 chance of being in one class or the other class, okay? Of course, like the perceptron, the logistic regression can accommodate any kind of vector with any dimension, mathematically, I mean. And what is the loss for that function? So there was a question, if you have a different activation function, you must have a different loss. The answer is absolutely yes. I will give you the loss without telling you where it comes from, because I had a couple of hidden slides with the kind of a proof of where it came from. In fact, we're going to assume, if we assume that our training data set follows a so-called Bernoulli distribution, so I don't know if you remember that from your statistic class, a Bernoulli distribution, and that you want to model your training data set from that Bernoulli distribution, and that model is called the likelihood, and you want to maximize this likelihood, and blah, 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 blah. After 2 pages of mathematical derivative, you come back to you arrive to a function that is like this one here, okay? Which is called, and that's a very important buzzword, the cross entropy. So those who have started playing with machine learning, maybe you've seen this, okay? Use the cross entropy loss, okay? And typically when people start playing around with deep learning, without quite understanding what they're doing, they see cross entropy, and then they go look at the math. They get an equation like this, have no idea where it comes from. But in fact, it comes from the fact that our machine, okay, maybe I will start talking about the machine, is a very good machine at estimating probabilities. And those probabilities, okay, so the output of my model is sigmoid of a dot product. this will be very close to this value here. So what is this? Okay, this is the probability of having class 1, and the pipe is what we call the condition. Okay, so the probability of class 1, given the fact that you fed it with x. Okay, probability, we call it a posterior probability density function. And Jeff Hinton, that you all maybe heard about, was asked 3 years ago by a journalist, how come machine learning are so good? Deep neural nets are so good, and he had to come up with just one line. He said those are wonderful machines for estimating conditional probabilities. Okay, now you kind of have the intuition what he meant by that. Okay, so you have a function that is very simple so far. We're going to make it more complicated in a couple of minutes, but at the end of the day, that machine estimates probability values. Okay, it tries to, at least. So it estimates, in a case of 2 class, it estimates that what is the probability of being in class 1. And if you want to know the probability of being in class 0, you just take 1 minus the probability of being in class 1. Okay? So in the other example, we got that the probability of being in class 1 was 12.5%. So the probability of being in class 0 is 87.5%. Okay? Because the sum of those two probabilities must be equal to 1. And so when you have 2 classes, you have this Bernoulli distribution that you can try to maximize. And at the end of the day, you end up having minus log of the output of your model, and we call this a cross-entropy loss. Okay? So I'm not going to get into too many details, because I have a little game at the end of the presentation. So if I can go through the end of the presentation, I will play a game that I call how can it go wrong? How can machine learning go wrong in medical imaging? So that's why I want to jump over a couple of mathematical details. So the beauty of that function here is that it is you can derive it with respect to W, and it gives that function. Again, usually my students have to prove this in a homework. It's not that complicated. So, and the beauty is that as opposed to the perceptron, see, it's a summation over every element of your data set, and there's no such thing like, if it is well trained, do nothing, right? And if it's ill trained, do something. Now it's take every element, and for each element, optimize your network. So that means this gradient is never going to be is never quite going to be 0. Okay? It will always try to reach a global minima. It will always try to improve your solution. So here's a little implementation I made some time ago. So as you can see here, there, and there, these are 3 results obtained with the perceptron. Those 3 results have a 0 loss. So that means the perceptron has stopped training. Whereas these are from exactly the same starting points. This is the result of a logistic regression, where at the end of the day, you pretty much always converge towards the same solution. So when you have data that are non-linearly separable, your logistic regression will eventually converge towards a good compromise between your 2 classes, and it will not, like the perceptron, oscillates like this. So how do we get to have to manage more than 2 classes? Well, we'll do exactly what we did with the perceptron, which is we'll have at the output of our network 3 neurons, each neuron being associated to a separation line, okay, so a classification function. But we need to have a different activation function. So the activation function is another very important buzzword called the Softmax. Okay, the Softmax is, at the end of the day, it's not that complicated. So what do we do? Okay, you take for each of your classes the dot product, which is a value between -infinity to +infinity. You take the exponential of that value, okay, exponential of this, and then you normalize it, okay? So that means mathematically you take exponential of your dot product for class I, then you normalize. So what will happen by doing this if you normalize? That means the sum, here I have 3 outputs, 3 classes. The sum of those 3 outputs is going to be equal to 1 because we normalize, right? And this can be seen as probability values, okay? It sums up to 1. And that's absolutely gorgeous because now you have a machine that if it is well trained, you can feed it with an input vector, and at the end it will give you what's the probability of being in class 1, what's the probability of being in class 2, what's the probability of being in class 3. And then you assign it the class with the largest probability, okay? As Hinton said, it's a wonderful machine for estimating posterior probability conditional function. This is a posterior probability density function. So this exponential followed by a normalization is called the softmax. Again, for those who have started playing with neural nets, maybe you've been told, okay, put a softmax at the end and put a cross entropy loss and select a stochastic gradient descent. See, those buzzwords are now trying to make sense, okay? Hopefully. Here's an example for more than 2 classes. This is a very famous CFAR10 dataset. So it's a dataset with 60,000 images. Each of those images have 32 by 32 pixels. They're all RGB images. We have 10 classes: airplane, automobile, bird, and so on and so forth. The class label could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It could be this, or it could be airplane, automobile, bird, and so on and so forth. But more mathematically, we'll use a one-hot vector. Okay, so that means the one-hot vector, we have 10 classes. So the one-hot vector, the ground truth, or the target, has zeros everywhere and a 1 for the correct class. Does that ring you a bell? 0 everywhere and a 1 somewhere? Okay. It's like I saw it's in the bell is written on a building close to here. It's a Dirac distribution function type of a thing. It's close to it. It's not exactly a Dirac. So it can be seen as a probability density function. Okay, 1 and 0 everywhere. So you have. So it's ground truth. Okay, we know it is true. So that means there's 100% chance this image is an airplane, and 0% chance to be anything else. And we have a machine that predicts probabilities. Okay, it will hopefully predict a large probability for airplane if it sees that image, and a low probability for the other ones. So we want the output of your model to be as close as possible to this one odd vector. Okay, and if you compute the mathematical distance between the two, this can be done with a cross entropy loss. It could also be done with a KL divergence. Maybe some knows about that. That's another loss. I'm just saying it exists. So the cross entropy loss, when you have multiple classes, is kind of like that. I'm not entering into too many details why there's a log associated to it. It's a little proof. It's not that complicated. My students have to prove it in the homework. No, this one I prove it on the board. And of course, that function, you can derive it. Okay, it gives that formula here. And you can implement a stochastic gradient descent to find a global minima. Okay, and once you find a global minima, now you have a machine that each time you feed it with some input value will output a probability for each class that you have. Okay, and the sum of every output of your model is going to be 1. If it's not 1, then you have a bug. Okay. Something else that was mentioned yesterday, I'm gonna give it a different flavor. Let's come back to this very simple example where we live in a 3-dimensional space. Here, let's say we have a point in this 3-dimensional feature space that is at position 1, 1, 1. And then you have 2 different solutions. A solution where the first parameter is equal to 1 and the other 2 parameters are equal to 0. And the second solution where all 3 parameters are equal to 1/3, 1/3, 1/3. These 2 different models, so these are those are the equations of of lines. So those two lines are different, but their score for that specific point are identical. Okay, if you take the dot product, in both cases, it's going to be 1. So there has to be a mean for discriminating between those two different solutions, saying one must be better than the other one. And one way of doing this is by adding a, well, okay, mathematically it's called the maximum a posteriori, but at the end of the day, instead of just minimizing the dot product, we're going to have plus lambda. Lambda is an hyperparameter times a regularization function. So that regularization function will essentially say that, well, among all of your solutions, we would like to have solutions whose values for those weights are as close to 0 as possible. This typically prevents from having overfitting. Okay? If you don't have that term on the right, this lambda times RW, and you just have a neural network with a lot of neurons with a large capacity, your neural network will have a natural tendency of overfitting on your data. If you say, well, and overfitting means what? It means that some parameters are very, very positive, like in the millions, and some other parameters have to compensate for this, or they're very, very negative. Okay? If you say, well, no, you're not allowed to have very positive values, very negative values. You should have values close to 0. Then you have a solution that is more linear type of a thing. Okay, so this is called a constant and the regularization term. As it was mentioned yesterday, the typical solutions, again, what you will implement, I think it's Thursday, or Friday, I don't remember. There's the day is your day, I think. The day where you're going to be Wednesday. Huh?
My day is Wednesday.
Your day is Wednesday. Okay, no. Yeah, they will implement those kinds of things probably. So you can yes and no. No regularization. Okay, no regularization. It's working anyway. Okay. Most of the time it doesn't work. Wednesday is going to work without the regularization. Okay, so we have this function. So lots of information. Let me recap this. So if we have two classes, you can implement a perceptron with a sigma sign activation function or a logistic regression with a sigmoid function. In the case of a logistic regression, you have a machine that predicts the probability of being class 1. If you have multiple classes, then you need to have as many output neurons as you have classes. For the perceptron, you will take the class with the largest score. And if you implement a logistic regression, you need to add a softmax activation function at the end, and that machine will estimate the conditional probability of being in one class or another class. We have the Perceptron Criterion, which is the first line, which is mathematically absolutely identical to the second line. Okay, the second line is the summation over each and every element, not just the wrongly classified, but at the end of the day, it gives the same loss in the first one. If you add a 1, this is called the hinge loss or the SVM loss. And you have the cross entropy. Okay, so if you have a logistic regression, you need to implement a cross entropy. And in K class, you have a similar picture. Okay, it's just with K classes. You have this loss function. Okay, you have to define the first loss function. Sometimes we call it the data term. Okay, so criterion, perceptron criterion, or the cross entropy, for example, plus lambda, an hyperparameter that you have to tune, manually tune, with a regularization function, typically the L1 loss or the L1 distance or the L2 distance. And you need an optimization function, which is a gradient descent that we typically implement. The one we typically implement is called the stochastic gradient descent. There are other methods. Christian tomorrow is going to be talking about momentum and Adam, I think, which are generalization of the stochastic gradient descent. Okay, now let's go deeper. Okay, deep learning, deep. Okay, so what is it? So it's, okay, spoiler alert, we're going to add neurons. Okay, it's just a matter of adding more neurons, adding more neurons, okay? Remember before when I said, okay, we might fall into a problem where we have data that is non-linearly separable. I said the first typical solution, just acquire more data, so more observations. The second one is to use a nonlinear classifier like decision tree. But there's a third solution that is very elegant, which is to take your data in the original feature space and project it to a new feature space where hopefully things are going to be linearly separable. This is what deep learning does, okay? So let's go back to where we were, okay? A 2D example. So points live in a 2D feature space. We have two classes here because we have just one neurons at the output. And that's a linear logistic regression. So the model essentially is a sigmoid of a dot product, okay? So the first set of nodes is called the input layer, okay? We'll call it, for the rest of the talk, we're going to be calling it the input layer. And the neuron, the single neuron, the only neuron that we have, we'll call it the output layer. The output, it's the most simplistic output layer one can think of, dot product plus a non-linearity. Okay, now let's add a few more things. So let's say we add 3 neurons, okay, like this, and it's not yet the output of our model. It's just 3 neurons that we added. So what is going on here, okay? We have 3 dot products, because that's what a neuron does. Neuron dot product, neuron dot product, neuron dot product. Okay, so we have 3 neurons, 3 dot products. Each neuron is associated to an activation function, so it's a non-linearity. So what is going to be the output of each of those neurons? It's going to be a value between 0 and +1 if the non-linearity is a sigmoid function, okay? So that means after this first layer, we have 3 values, okay? So it's a vector that lives in a 3-dimensional space, okay? The output of the first neuron is a real value, output of the second neuron is a real value, and the output of the third neuron is a real value. So it's a vector in 3-dimensional space. Okay, good. So that means the output of this neuron is what? So we have 3 nodes as input, 3 neurons. So that means we have 3 by 3 parameters, so 9 parameters, that we can store mathematically into a matrix. And that matrix, if we multiply it with the input vector and then feed it to a sigmoid, this will give us 3 real values. Okay, it's going to be the output of our first layer. Okay, we haven't classified nothing yet. Okay, it's just like we're playing around. Okay, so for simplicity, I'll be making reference to it like that. So the output of the first layer is a nonlinearity function. So far, it's the sigmoid. It could be another one, but let's say for now, we'll use the sigmoid, and it's matrix W time vector X. So that will, matrix W time vector X is like 3 dot products, but mathematically it's the same as multiplying a matrix with a vector. So it's going to be a 3-dimensional vector, and this 3-dimensional vector is going to be fed to sigma. Now let's say we want to do this. We have 2-dimensional data, we have a 2-class classifier, okay? And we have 1 hidden layer. So we have the input layer, 3 neurons, 1 for the bias, the other 2 for the features. Then we have 9 parameters, 3 neurons. The output of those 3 neurons is what? It's a vector in a 3-dimensional space. And then we want to have a 2-class prediction. So I'm going to add a neuron at the end. So this neuron here. So what does this neuron do? It will take W0 with the subscript 1 here because it's the, so that the subscript 0 means you're in the, in the first layer. The subscript 1 means you're in the second layer. So you'll take this parameter W0 times the output of that neuron plus this parameter times the output of that neuron plus this parameter times the output of that neuron. Okay, it's a dot product. If it's a dot product, then it's a linear classifier. okay? So that neuron here, so that last neuron here, it does a dot product, and the result of that product is fed to a nonlinearity, a sigmoid, okay? So mathematically, this overall system will try to mimic this function, sigmoid of a dot product between W1, vector W1, times the output of the first layer, which is sigmoid of W0 times X, okay? And so the output of, this is where things get nasty, okay? So the output of this network is a real value between 0 and 1, okay? It's still predicting the probability, it's the 2 class, okay? It's still making a prediction of what is the probability of being in class 1. Okay, so here we have an input layer, a hidden layer with 3 neurons, and one output layer, 1 neuron. So usually when you look at presentations and you go in the literature, you rarely have a representation like this because it's visually very bulky. So usually we have a representation like that. Just so we have those nodes here, those nodes, and then the links. And I'll be representing the weights here by a matrix W, and here the weights by a vector W, okay? So here it's a 3 by 3 matrix, and here it's a 3 by 1 matrix. 3 by 1 matrix is a vector, okay? And red here, it's just a visual representation to say, well, red means it's the output neuron, okay? Yellow means it's some hidden layer neuron, and green means it's an input node. Okay, that's what we have. Here, this is, at the output, it's a linear classifier. So if it's a linear classifier, I can add a bias, okay? Linear classifier means I'm gonna fit into a certain dimensional space an hyperplane. And this hyperplane, if I don't want it to be forced to be passing through the origin, I can add a bias. Do you add a bias in your implementation? I hope yes. Yes, he says yes. Good. Okay, so this network contains a total of 13 parameters, okay? So 9 parameters between the input layer and the hidden layer, okay, because we have 9 connections. Each connection comes with a parameter. And then 4 parameters between the hidden layer and the output layer, okay? So it's a 13 parameter neural network. And already I cannot picture what the loss function would look like with respect to 13 dimensions. It's already too big. It's not very big, okay? It's very, it's a humble neural network. So I can increase the capacity of the model, okay? Increasing the capacity of the model means what? It means that the model will be able to adapt to different types of nonlinearity function, okay? And here you already have the feeling that if you look at the output, since sigma is a nonlinearity and the other sigma is yet another nonlinearity, and that means this function that sometimes we call a general function, it can fit onto data that is nonlinearly separable, okay? So by adding more layer, you'll add more capacity. More capacity, that means that your model will be able to eventually fit onto data that is really not linearly separable. Okay, that goes like this, right? Here, I start to, increase the number of neurons in the hidden layer. So how many parameters did I have in this network? Well, I have 3 input nodes times 1, 2, 3, 4, 5. 3 times 5 is 15, plus 6 times 1, so 15 plus 6, 21 parameters. Okay, so we have a network of 21 parameters to train. So how do we get to train it? Well, we need to have a loss function. What kind of loss function can we use? In this case, the output is a sigmoid. It can be a cross-entropy loss. If it's a cross-entropy loss, If you have the cross entropy loss, you can compute a derivative. If you can compute a derivative, you can implement a stochastic gradient descent. Okay. So it's, you know, everything flows to where we are. So here's an example so this is a very nice website. What time is it now?
Yeah, Pierre-Marc, maybe if we want to let sometimes to
Okay.
question just
Yeah.
before the pause. I don't want to cut you, but if you
You
think
don't want to
it's a
cut me,
good-
but you will cut me.
Yeah.
Okay.
If you think it's a good time, or I let you to
Okay,
conclude
maybe
on
I can
that.
finish with this,
Yeah, okay, for
and
sure.
then we can go for the break. Yes?
Well, but there will be some
Oh, for
questions.
some
so
questions.
that's
Okay,
why
so
we want
let's
to let some
let's.
questions.
I just want to show you this. So here is what we have. Okay, we have two different classes of points that live in a two-dimensional feature space, because that way we can picture what's going on. On the far left, we have no hidden neuron. Without no hidden neuron, so it's like a perceptron. So with just one neuron, so that means you have a linear classifier. So as you can see, we can just cut the feature space in two separate regions with a linear function. And in this case, your model has a low capacity and thus underfit your data. Okay, so the result is going to be probably very bad. In this case, you'll probably have an accuracy of 50%, which is catastrophically low. In the second case, I've created a neural network with one hidden layer with 12 neurons in it. And as you can see, it's not perfect, but it kind of fits the twirl. And when you add up to 60 hidden neurons, then you start having what we call problem of overfitting, because the neural network, see those two red dots right there, this red dot, that red dot, and those two green dots. I've put it there just for the sake of illustration, but these can be seen as outliers. Okay, like a patient that looks sick but that is not sick, or it could be the other way around. Okay, that looks super healthy but in reality is sick. Okay, so you have points that are outliers. They're not supposed to be there, but they are actually there. And so your network has so much capacity that tries to have a minimum loss, and you can only reach a minimum loss on a training data by classifying correctly every sample. But that's bad, because when you see new green dots in that area and new red dots in that area, those new dots are going to be poorly classified, wrongly classified. And so your model is not going to generalize well. Okay? So your model is going to overfit. So this is a very typical problem with neural network. They have such a capacity, and it's very easy, just add more neurons, more neurons, more capacity. So if you want to prevent this from happening, you add a regularization term, okay? The lambda plus RW. So if you have this, and you see that you're overfitting, well, increase lambda. You're still overfitting, increase lambda even more, and eventually you'll reach a point, you'll reach a situation like the one in the middle, okay? Okay, now questions? Okay, not too, question not too complicated, please.
So
I can
complicated
answer.
question right now. Is there someone who wants to ask something?
Hello, sir.
Hi.
I have a question about activation function.
Yes, yes.
So, if we put the Softmax and the Sigmoid function both into the binary classification, what's the difference about them?
Okay, what you're saying is that, let's say you're doing two-class, so you have a two-class problem.
Yes. So
So either you can have a situation like this one where you have a sigmoid function at the end, or you could have two neurons with a softmax. Is that correct? Neuron for class 1, neuron for class 2. Is that correct?
Yeah.
Well, if you have this second, some people, including some of my students, and I keep telling them, don't do that, and they listen to me. They usually backtrack, and so when it's always better when you have a two-class problem to have just one neuron at the end. Okay. Of course, if you have two different neurons, it's going to work because you're going to have a system that will measure the probability of being class 1, the probability of being class 2. But mathematically, it means that you'll be trying to fit. I knew I would have to do it. Okay. Okay. Say you have points like this and points like that, and you want to separate it. So if you have two neurons at the output, each neuron is a dot product. So that means you'll try to learn one separation plane like this, and yet another separation plane like that. You can have just one separation plane, it will do the job also. Okay? If you have two separation planes, that means you will have more parameters in your model, and the more parameters that you have usually is it leads to some more problems. Okay, so you have more parameters. It means it's more memory, more computation, and so on and so forth. So it's going to work. I mean, if you have a situation like that, you're learning two hyperplanes that just look like this in opposite direction. It will work, but it's kind of overkill solution. And in fact, that's very funny that you're saying this because in one slide, I copy-pasted a figure from an archive paper that was published last year, and this is exactly what they're doing.
Okay, thank you.
They're not my students, so there's nothing I can do about it.
Thank you. Other questions?
Sorry. Hi.
Hi, that's a great presentation, thanks.
Thank you.
The tricky part, of course, is knowing when knowing when to stop. If you go back to the last slide with the overfitting in cases where you can't visualize what's happening. I mean, one way to do that is to use, as was discussed yesterday, use different test sets and so forth.
Absolutely.
Very
Validation sets, yes.
Yeah.
Typically, your test set, you're supposed to validate, to just look at it once.
Yeah.
But
and
yes, you're
it's
absolutely right. You have a training data set and a validation data set.
Yeah.
And the result that you should be always looking at should be the result on the validation set.
Yeah. So it's expensive and you run out of data, but I'm just wondering if so from what you were just saying then about increasing lambda, are you suggesting increasing lambda until the system fails and then backstepping a bit? Is that a...
When you're looking at the training data set?
Yeah, yeah.
Yes. This is something that is often made. In fact, it's something that is always made. These are hyperparameters. And when you're, so lambda is an hyperparameter.
Yeah.
The learning rate is another hyperparameter. So you have a plethora of hyperparameters. And typically, you will want to find what are the best hyperparameters for your system. And you do this by playing with your training data set and look at how it generalize, how well does it generalize on the validation set. So if your system completely overfitted on your training set, it will perform poorly on the validation set. So you know that there's too much capacity, there's something you have to do about it. But you never look at the test set in principle. Like for example, with Olivier, we organized some time ago a challenge, a Kazakh segmentation challenge. And the challengers are invited to, process our test data. All they have are the images. They don't have the ground truth for the test set. And they are allowed to submit their result 3 times. So you can submit the first time. If you're unsatisfied, we give you a second chance. And then you have to choose which one is best. So you submit a 3rd time, okay? But not more than this. Because otherwise, what will happen, you will kind of optimize your system so it best perform on the test set. So this is like cheating a little bit.
Thank you. Maybe we have time for a last quick question, otherwise we go for coffee. Yeah, okay. Last question.
Well, thank you for the presentation. You mentioned at the start that you always need to have complete data sets, so all the patients, for example, have the same exams that are made.
Yeah. They follow the same,
the same protocol.
acquisition protocol, yes.
Well, in medical studies, you often have missing data. How do
Yes.
you deal with that
In the
deep
basic
learning?
in the basic machine learning world, there's nothing to do about it. This is data you cannot play with. However, it's the topic of research. In fact, what do you do when you're missing data? So for example, let's say you're processing images. Okay, you're processing MRI images, and those images from those patients come from different hospitals. They don't have the same acquisition protocol because those are patients that come from the clinic. And so maybe some patients has a T1 and a T2 image in one hospital. In other hospital, they have T1, T2 and flare, and maybe in some other hospital, they have T1, T2. They don't have flare, but they have proton density type of a thing. So you have lots of data, so you have lots of patients, but they don't live in the same feature space type of a thing. So one possibility, there was a couple of papers working on this. How can you just take the data and try to mimic or replicate a missing modality? Okay, there's obviously at the end of the day you'll have a suboptimal solution. The optimal solution is to have the same protocol all over the place, but this is one thing you can do. And often it is done with so-called generative models, like variational autoencoders or GANs, something like that. But honestly, if your patients or your data did not come from the same protocol, you're in trouble. That's all I can say. And it's a very fascinating research topic. So because there's no obvious answer to that question, but it's a very good question. Maybe it's is it the topic of your PhD or no? Okay.
He's no more in PhD. In fact.
Huh?
He's no more in PhD.
He's no more in PhD.
Yeah,
Okay.
yeah. He's a young man, but no. Okay, let's go for the coffee break and go back at 11. Thank you.